Now, using the ideas of simple interest, we're going to expound upon that and come up with a new system of interest called compound interest. Basically, the idea is instead of just applying the interest one time at the end of a period of time, so like, if you were to deposit money into a savings account and then withdraw all of that money at the end, they apply the interest one time at that moment of withdrawal. Instead of doing that, the interest is applied periodically throughout the course of that account, or the lifespan of that account, so to speak. And so this could be a monthly accrual of interest, or an annual accrual of interest, or a weekly, or who knows, some division of time. And so you earn interest back into the account over these time periods, or at the end of each intermediate time period. And then what ends up happening is that the next time period you earn interest not only on the original principal but also on the interest that was put back in. And so it allows the account to grow faster because your interest is being calculated on a larger value over time, a larger principal, right? The original principal plus the previous interest is what you then calculate the next interest from, if that makes sense. Hopefully it does. So anyway, that's your compound interest idea. So you're continually getting interest put back into your account so that over the next time period you earn interest on that interest and the original principal. So that's compound interest. Now, how does that relate to simple interest? Well, simple interest, we know I equals PRT, and the future value is just taking that interest and adding it back onto the original principal, okay? Now, if I were to do this, and of course this is over T years, if I were to, and we've done this derivation in the simple interest section, but I just want to rehash it a little bit here. Again, if you were to take this expression, plug it in for I, you get P plus PRT. And then we've talked about you factor out the P because it's a common factor, and you get 1 plus RT as the remaining factor. Okay, so P times 1 plus RT. And of course, you could redistribute that P in to get this expression. So factoring it out is the opposite, so to speak, of distributing it in. Now, if I were to consider this as an annual compounding, so the bank gives you interest at the end of the first year. So T is 1, right? T would be 1 year. So after 1 year, A is equal to P times 1 plus R, right? The T value is just 1. Now let's say, that would be the case if you were just to withdraw the money after 1 year exactly, okay? This is how much you would have in the account. But let's say after a second, you left your money in there, they applied the interest at the end of the first year, and then after the second year, they apply another interest. So this is an annual compounding. Rather than withdrawing the money at the end of that first year, you leave it in, and now you're accruing interest on the original principal and the new interest. Okay, so you're getting more and more interest. Well, let's say that happens. Then what do? After the second year, 1 year? How about first year and second year? That's better. That looks kind of weird. After the second year, then you get the original, so the amount this becomes the new principal, and then you apply another factor of 1 plus R to that, okay? So you're multiplying by that same rate, essentially. And so what you end up with is P times 1 plus R squared, okay? First year, that has a 1 power on it. Now, if I were to do this after the second year, or third year, and you can kind of see how this is going to build up. The new principal is P times 1 plus R times 1 plus R. That's the new principal. That's what's in the account beginning the third year. And then at the end of the third year, you multiply by another factor of 1 plus R. Again, you multiply by the rate again to the prior amount that's in the account, and you get the new final value, okay? And now that simplifies to 1 plus R to the third power, because you've got three factors of the same thing, right? Anything times itself where there's three factors is that thing to the third power. And so now what I want you to notice is that there's a correlation between the power and the year, okay? And so if you were to continue this after t years, or after, I should say, the teeth year, not teeth my mouth, but like the teeth year, if that makes any sense. I'm just trying to keep consistent. The teeth year, does that make any sense? I don't know, it makes sense in my mind. Then what you end up with is P times 1 plus R times 1 plus R times 1 plus R, and there would have to be T factors of that 1 plus R, right? You just keep putting a 1 plus R in as a multiplier until you get down to this last year. Well, that's T different factors means it's a T exponent, so you're going to get P times 1 plus R to the teeth power. Teeth power. Anyway, terrible. Bad pun. Don't laugh. P times 1 plus R to the T. This is the formula for compounding annually. It's an annual compounding interest. Okay, so annual compound interest is just this formula: A equals P times 1 plus R raised to the T power. All right. Okay, now from there we can derive another formula. Let's say you wanted to compound monthly or weekly or daily or semi-annually or some other fraction of a year, not a full year, okay, but a fraction of a year. So you're actually getting interest paid in more often than just once every year. Well, we can make an adjustment to this formula. We can tweak it, but it's going to take two adjustments, okay? The two adjustments, and let me erase some of this derivation here. Now we have our formula, so in fact I'm going to write it up here. Annual compound interest. So A equals P times 1 plus R raised to the T power, all right? Make sure that's right, yep, okay. So now, the two adjustments we're going to make, if you want N compounds per year, so that could be, if it's monthly compounding, that's 12, N is 12 times per year. If it's daily compounding, it's 365 times per year, okay? So if it's N compounds per year, then what you have to do is you have to take the annual interest rate, cut it down by that number of compounds. So say it's monthly compounding, then you would have to take 1/12 of the interest rate and apply it each month, okay? So you have to divide the R by that N value. If it's daily compounding, you take 1/365th of the rate and apply it each day, all right? So that's the first adjustment, is you get the rate divided by N, okay? You have to take 1/n of the rate and apply it over that period. Then the number of times you actually have to multiply by this factor isn't just t times. It's not just at the end of every year. It's actually at the end of every compound. And so every compounding period, I should say. And so, for instance, if you're compounding, if it's again 12 times per year, then at the end of 1 year, if t is 1, you should really have a 12 up here as your exponent because you're applying it 12 times, once each month. And so what you end up with is multiplying the t by the number of compounds, because the exponent should be the total number of compounds that existed over the lifespan of that account. So you would want n times t in the exponent. Okay, so you just have more factors of the 1 plus r over n attributing to the growth of that account. Okay, and so this new formula with those two adjustments, division by n in the rate, multiplication by n in the exponent, is going to be our formula, our general formula for n compounds per year. Now again, n can be a number of different values, and maybe I'll write a few of them up here, but if it compounds annually, so let's see, actually let's do this in another color so that it stands out. So compounds and the n value, corresponding n value. So if it compounds annually, well, that's one time, right? N is one time per year. If it's semi-annually, then the n value is 2. You could do quarterly. And of course, these aren't all of the possible n values, right? I skipped 3. You could, in theory, have every third of the year or something. But anyway, these are some popular ones, I should say. So annual, semi-annual, quarterly. You might see monthly. Monthly is a 12. Weekly. There are 52 weeks in a year, plus a day, I think, or plus 2 days, something like that, plus 1 day, I think. Anyway, so it's slightly off from 52, but close enough. And let's see, weekly, we could do daily, right? Daily compounding is 365 days in a year. If you're using the banker's rule that we talked about in a previous video, that could be 360, but I'm going to go with 365 in our case. And you could even go more than this, and it gets kind of ridiculous. You could, in theory, go with hourly compounding. So you get interest applied to your account every hour of the year. And this one I'm going to need my calculator because I don't remember all these values. But how many hours are in a year? Well, you take the number of days, 365, and multiply it by 24 hours. Now, technically, the number of days is 364 and around a quarter, but I'm not going to deal with the little decimals and stuff. We're just going to stick to whole numbers here. So hourly, there's about 8760, right? 8,760 hours in a year. And if I wanted to go minutely, of course, you can see where this is going. Minutely, the n value is at 8760, then times 60, because there's 60 minutes in an hour. And you get, I need a little more space. N is going to be 525,600 minutes in a year. And of course, if you wanted secondly, well, the n value is, what's that times 60? 31,536,000 seconds in a year. You could go tenths of a secondly, I don't know, nanosecondly. You could really get this small. Ultimately, let's say you just went with, you approached infinity. You wanted an infinite number of compounds. Every moment, we'll call it momently. I don't know. I'm making up words here. Every moment of the year, so an infinitely dense compoundings. I shouldn't put infinite there. That's the n value. The n value approaches infinity. Okay, it doesn't ever hit infinity because infinity is not a number we can attain, but we call that continuous compounding. Oops, I can't spell right either. Continuously. There we go. Continuously compounding. Okay, I get it straight. Anyway, so we have this continuous compounding situation, which is every moment of the year, an infinite number of times, essentially. Now I can't just take. What I could do is I can take any of these other finite n values and plug them into my formula here in those two places for n. That's doable. Gets complicated when you start plugging 31 million in, right? But 12 is a nice one. 4 is a nice one, right? Those you can plug in. I'm just doing this to be goofy. Although these are real values you could use. But I'm really just trying to motivate the infinite idea. So the infinity there, you can't just plug in infinity, right? You can't divide by infinity. It doesn't make any sense. You can't multiply by infinity. It doesn't really make sense. Infinity is not a number you can do things with. However, we can, using some clever calculus, which we're not going to get into the details, you can explore properties of functions or of equations where values approach infinity. What do they become? What do they act like? And the compound interest formula, as this n value approaches infinity, behaves like a new function. And I'll write the new equation, I should say, not function. P times e to the RT. Now, I won't go through all the details of where that comes from, but it's really cool, actually. It's a bit beyond the scope of this course, but if you want to look up something I think is really neat, I kind of geek out studying this kind of stuff, but it's very neat where that formula comes from, how this and this relate. Now what the heck is the e in there? E is a new variable. It's not actually a variable, it's actually a number. It's the number e. E Now you're thinking, that's not a number, it's a letter. It's a number. All numbers, everything we write, the number 52 is just a symbol. What I wrote here is just a symbol that represents a concept of 52, whatever 52 is. Well, this is just a symbol that represents a number that we call E, Euler's number. E stands for Euler, E-U-L-E-R. I don't know how you spell Euler, but it starts with an E. Anyway, Euler was a mathematician, came up with this idea. So anyway, I won't go into the details there. Too long for this video. But anyway, the value of E, and I always get the decimals messed up, but it's it's approximately 2.7182818 It's a bunch of stuff. There's lots of decimals there. What you'll find is in the actual value of E, there's no consistently repetitive pattern in those decimals. There's also no terminating point in those decimals. It's an infinite length of decimals with no repeating pattern. Even though it looks like there's a 281 kind of pattern there, it doesn't. It doesn't continue beyond a couple digits here. And so this is what we call an irrational number. We've talked about irrational numbers before. Kind of like the number pi or the number square root of 2. Lots of irrational numbers. This is an irrational number. It cannot be written as a fraction with integers. Okay? Irrational number. There you go. Okay. Now, that value of E, again, it's really neat how this formula transforms into this one with an irrational number in it. But if you're interested in that sort of thing, which I would be, check it out. You can do a little research on your own on that, but that's kind of cool. Anyway, compounding interest, we're going to use this formula for continuous compounding. All right, so that gives us a few really neat examples how to derive the formulas and what the formulas are. Now we're going to go through in the next few videos and come up with some examples on how to use particularly these last two formulas on compounding interest and continuous compounding interest.